Good afternoon, everyone, and welcome to your AP Physics 2 Prep Week session. Today, we'll be taking a look at yesterday's questions and working through those. So welcome back. Prep Week Day 2, our overview for the day, our agenda is to take a quick look at question 1 and work through its solutions. Then take a look at question 2 and work through its solutions. Then do a debrief and summary and give you some advice for the AP exam. And right before we get into that, we'll be showing you the College Board's AP 2020 exam walkthrough, so you know exactly what to expect as you log in. I am Joe Mancino from Glastonbury High School in lovely Glastonbury, Connecticut.
And I'm Brendan Eaton from Reedy High School in Frisco, Texas.
All right, so here is your exam walkthrough. It's just going to take me a minute to swap the share over. Just be a moment.
This video will walk you through the AP 2020 exam's important steps and offer tips. 2 days before the exam, you will get an email with your AP ID and an e-ticket that will take you to your personalized exam. Check in 30 minutes before your exam starts. The first thing you'll do is enter your 8-character AP ID and then fill out all your personal information. Note the timer at the bottom of the screen. Hit continue. The exam will automatically start when that countdown hits 0. And once it starts, the timer located at the bottom will count down how much time you have to read your question, craft your response, and submit it. If your exam has 1 question, you will have 50 minutes. If you have 2 questions, you will get 30 minutes for the first one and 20 minutes for the second one. If you are approved for extended time, it will be added automatically. The timer will turn red when you have 5 minutes left. That's when you should wrap up your work and start submitting your response. Once that timer hits 0, you will automatically be moved to the next question. This is important. You can get partial credit for a partial answer, but you will not get any credit if you submit nothing. You can use any device to take this exam: a desktop, laptop, tablet, or phone. If you're typing on a desktop or laptop, you can reduce the size of your browser window so you can see the question and your text file side by side. Type your AP ID and initials at the top of the page. You can also write your responses on paper. If you're writing by hand, use a number 2 pencil or a pen with blue or black ink. Use white paper, lined or unlined, and write legibly. Print or cursive is fine. You can place your phone next to your paper so you can keep an eye on your time. Be sure you put your AP ID and initials at the top of the page. If you use more than 1 piece of paper, number each page in order. For most AP exams, there are 3 ways to submit work. You can attach a text file typed in another application. You can paste a response typed in another application, or you can attach photos of work you wrote by hand. Let's walk through each option. To attach a typed response, click Attach Response with Attach Text File. You can browse for a file. Once you hit Submit, you cannot go back to that question, so make sure you're ready to move on before you hit Submit. If you choose to copy and paste your work, click on Paste Response. Copy your response and paste it into the box. Review it to make sure it has everything you want to submit and is formatted correctly. Once you have checked the pasted copy, hit Submit. If you're attaching a handwritten response, tap Attach Response. Tap Attach a Photo. Make sure it is vertical and you are in a well-lit space. Snap your photo. If your response has more than 1 page, make sure you attach the pages in order. Remember, once you hit Submit, you cannot go back. If you just have 1 question for your exam, that's it, you're done. For exams with 2 questions, if you finish the first one with time to spare, a timer will start a countdown for when your second question will automatically start. When you see this screen, the timer has started for your second question. The process for answering question number 2 is exactly the same as for question number 1, except you have 20 minutes to read the question, work on your response, and submit it. Once you submit your second answer, you're done. Some AP courses like World Languages and Music Theory will have exams that work a little differently. To learn more about these courses and more details on AP 2020 exams, go to cb.org/AP2020.
All righty. So that is a quick summary of everything that you need to know for this year's exams, which certainly are going to be a little bit unusual. Okay, today our focus is on the questions that you solved yesterday with Mr. Eaton. So I'm going to be walking you through question 1, and he'll be taking you through question 2. In question 1, your task was to take a look at this pair of charged spheres and answer some questions about them. Around those spheres are drawn some equipotential lines, and we had looked at a similar question to this in the AP live stream when we did electrostatics. First, there's just a description of the setup. There are 2 charges, X and Y, and there are these lines of equal electric potential curves, rather, drawn around the charges. Not a ton of information, but we are told that the microphone here. We are
told that the outer line has a potential of 10 volts, and that there's an increase of 5 volts for every equipotential. We're also told that one of the charges is positive. And your job is to figure out all the rest of it. So first off, we're asked, what is the potential at point A, point B, and point C? Well, we only know the potential of the outermost line. We're told that that's 10 volts, but we're also told that there's 5 volts between every line. So if the outermost line is 10 volts, and point A is on the next line in, point A is at a potential of 15 volts. Point B is 2 lines closer to the charge. So from 15, it's 20, then 25 volts. So point B is at 25 volts of potential. Point C, which is 2 more equipotential lines closer, is at 35 volts. So there are the solutions. And the justification is that each line is 5 volts more potential. All right. The follow-up question, part B, asked, well, which charge X or charge Y, which sphere has greater charge? Does X have greater charge, or does Y have greater charge? And all we have to go on is this diagram, and that's it. So in my justification, I took a look at where the closest ISO lines were and figured out what their value was. For charge C, I can see if charge C is at a potential of 35 volts, that innermost line is at 45 volts. For charge Y, the innermost line, which is also at 45 volts, is way closer to sphere Y. So I said that since sphere X and sphere Y have those 45 volt equipotential lines, we can judge by the placement of the lines which one has greater charge. So sphere X has its 45 volt line much farther away than sphere Y does. Well, I know that the potential at that distance depends on the amount of charge. So for sphere Y, at a small distance, there's a potential of 45 volts. And for sphere X, at a significantly greater distance, there's a potential of 45 volts. So since potential is K Q over R, I know that the ratio of Q over R is going to be the same at those equipotential lines. So for sphere X, it makes a lot more sense that X has greater potential, X has greater charge in order to make a 45 volt potential at a greater distance. So X is definitely more charged. Question B also asked what the sign was of both charges. Now we only know that X is positive. We're not told any information about Y. But Y is also positive. There's no point between them where the potential is 0. So if your answer referenced the characteristic shape of the equipotentials, or the fact that there is no point between them where the potential is 0, both of those are really good arguments for part B. Oh, my mistake. I will fix that in just one moment. Okay. So as you see here, this is my response for part B, citing both the reason why charge X has more charge and the reason why I know that charge Y is also positive. Okay. Question C tells us the isolines of gravitational potential have shapes similar to those of the isolines shown, and we're asked to explain why these two sets of isolines have similar shapes. If we were to draw gravitational isolines or electric potential isolines, both would have the same shape. And there are a few reasons for that work. One, you could talk about what isolines tell you about the motion of affected particles. So the path that a particle would take if it were affected by the electric field of these two charges would always be perpendicular to the isolines if we were to release it from rest. And that's also true of gravitational isolines. So isolines, both of electric potential and gravitational potential, tell us which way things fall, for lack of a better word. And that's one good argument. The other argument would be the isolines are perpendicular to the electric field lines in the same way that gravitational isolines are perpendicular to the gravitational field lines. And that would also be good too. You could similarly discuss the similarities in the equations themselves. It would be more challenging to talk about the similarities in the equations themselves on the 2020 exam, so I would discuss either the effect that both electric and gravitational fields have on nearby objects, or the way that isolines give us a clue about the shape of electric and gravitational fields. If you feel compelled to type or write an equation using any of those methods that you saw outlined in the video, do your best to describe the equation that you're trying to refer to. If you're typing, there is no way to embed an image in what you're typing. But if you say E equals KQ over R squared, and seriously, write the word squared, that's fine. You can write a caret with a 2, and that's fine. Anytime that you really feel compelled to use an equation as part of your argument, go ahead and use it. The readers will understand what you're writing as long as what you're writing is recognizable as the equation that you're trying to write. However, on the AP Physics 2 exam, it is extraordinarily unlikely that you will want to write an equation. That's simply the way the questions are written. All right, a proton with charge of plus q and mass m is released from point B. Describe how the magnitude of the acceleration of that proton changes after being released, and explain your reasoning relating it to these equipotential lines. I just said that acceleration is proportional to force, and that the magnitude of the force decreases as the proton is pushed away. So there's less force, so there's less acceleration. I can tell that the force decreases because the equipotential lines are farther apart. And that means that the electric field is decreasing. So further apart equipotentials mean less electric field, less electric force, and less force means less acceleration. Sometime after being released, the proton has moved through a potential difference of 20 volts. Students are discussing how and why the kinetic energy of the proton would change after it's released. So student 1 makes this statement and student 2 makes this statement. And your job was to evaluate whether those students' statements were correct and then explain why. Well, student 1 is correct. Student 1 is correct because if the system contains all of the objects that they're talking about, the proton and the spheres, then the increase in the proton's kinetic energy is due to a change in the system's potential energy. So that student is giving an argument about the conservation of energy, and they've defined the system really well. So student 1, nice job. Let's take a look at student 2. If the system is defined as only the proton, its kinetic energy increases because positive work is done by the electric field. That's also correct. If the system is just the proton and its kinetic energy increases, then something is doing work on that proton. And the thing doing work is the electric field created by those two positive spheres. So both students were correct. All right, let's take a look at the graph. The spheres are separated by 15 centimeters. A student sketches this graph of the electric field as a function of distance along the line that joins the two spheres. State one aspect of the graph that correctly represents the electric field and explain your reasoning. The electric field is directed to the right near point X and directed to the left near point Y. I thought that was pretty good. I thought that was a good aspect of the graph because the electric field is directed away from positive charges. Oh, that says incorrectly. I apologize. There. So what correctly this graph shows is that the electric field is directed in the right direction. It shows the electric field pointing away from point X and away from point Y, and that's great. What is incorrect is that it shows a greater magnitude of electric field near point Y, but point Y has less charge than point X. So I know that that can't be right. So on the incorrect, the magnitudes are wrong. It should show a much stronger electric field near point X than it does near point Y. Remember, the magnitude of the electric field is related to the density of the field lines. And the density of the field lines very close to point X was much higher than the density of the field lines near point Y. And now, with question 2, your very own Mr. Eden.
I wish there was applause or something. That was a fantastic job. Thank you, Mr. Mancino. So question 2, this is your short question that we gave you yesterday. It's entirely based off of fluids, but it does have some ideas of energy kind of built into it, aka Bernoulli's principles. And we can kind of solve this a couple of different ways. But let's take a look at what we have. You have a nice little faucet that you kind of open it up, and water's flowing from left to right, and it's flowing through that section of pipe left to right. And if you notice, when you get towards point B, the diameter decreases, but point B is also at a greater height than point A is on the diagram. So where the pipe ends on the right, it exits vertically into the bottom of a large, deep pool. I'll tell you ahead of time, the fact that it empties into the bottom of a large, deep pool is completely irrelevant. And you're really just asked to define what's happening at point A and point B. So before we go into what section A was asking you, just take a couple of notes. The big take-home messages from this is that point A and point B are at different heights. B is at a greater height than A, and that B has a smaller diameter than A does. So when I see things that are at two different heights, I think Bernoulli. When I think they're two different diameters, I think continuity. And you could actually go either one of those two methods on this particular question. And you're about to see my notes on part A. Let's see what part A says. Part A says that there's a bubble of air at point A and later at point B, and it doesn't change temperature. Temperature stays constant. So in a paragraph, skipping through a whole bunch of words here, state whether the volume of the bubble at point B is greater, less, or equal to the volume of the bubble at point A. All right, so hopefully you've got your work with you that you kind of took some notes on as you went through, and you're kind of checking it as we go through. We're not really defining points here, but we want to make sure that you got the general idea and the details that go along with it as far as a good response is concerned. All right, so as far as what the answer is, I know you want to know what the answer is. At point B, the volume of the bubble is larger. And here's some notes that you see on your screen as to why the volume is larger of the bubble. So on the first bullet point, you can see that pressure is lower at B because it's at a greater height. That's using the idea of Bernoulli. You're changing height, so you have to have a change in pressure somehow, some way. Or you could say with continuity, because the diameter of the pipe is smaller, the fluid has to be moving faster. And if it moves faster, then pressure has to be lower. And in all honesty, I would have gone with continuity on this just to make it quick and easy as far as my response is concerned. All right, the second bullet point says that pressure and volume are inversely proportional. That means that if pressure is doubled, volume is cut in half. If pressure is quadrupled, volume is cut by 4. Now, knowing that idea, if the pressure is decreasing at B because the area of the pipe is smaller, the diameter of the pipe is smaller due to continuity, it's moving faster, pressure goes down. And if pressure goes down, then volume has to increase. And again, I want to point out that diagram has numbers on it. At no point did we answer anything about numbers. This is all about the concept as to what's happening to the volume as the pressure changes. Why does the pressure change? Well, the diameter is changing, or you can say the height's changing. So connecting all of those concepts gives you a really solid answer for part A. Okay, let's look at part B. Part B says, suppose instead the pipe remained a constant diameter. I do not have the diagram that shows the pipe of the same diameter, so I didn't put the old diagram. I didn't want to confuse you. So in this case, the diameter is exactly the same all throughout the pipe. Now, when I read this the first time, the first thing that I thought of was, wait a second, if it's a constant diameter, what has to hold true in this case? Well, continuity says that A1V1 equals A2V2. So if the cross-sectional area is not changing, well, the velocity of the fluid has to be the same. So what would the difference in pressure between points A and B be greater than, or would they be less than, or would they be equal to the difference in pressure between points A and B, as in part A? So here's what happens. The first thing that you needed to have said was that the speed of the water doesn't change. And again, that's because the cross-sectional area of the pipe is not changing. Now, in the previous example, in the first diagram, when the pipe did get smaller, part of our justification said that the fluid was moving faster at point B. And if it's moving faster, pressure decreases. Well, in this case, the water is not accelerating. It's not speeding up. So the change in pressure only has to do work to lift the fluid to point B instead of also doing work to speed the fluid up. So again, in this case, the difference in pressure now is smaller than it was in situation A. Okay, and let's take a look at part C. You have a triangular prism. I don't know what the point of saying it's a triangular prism is. It could really just be about any object. But again, that's to get you thinking about things that are important as far as the wording on the question actually is. Okay, so it's suspended in a tank of water while suspended from a rope without touching the bottom of the tank, as shown in figure 1. Notice it says not touching the bottom of the tank. So that means that there is no normal force from the bottom of the tank. If you were to draw a free body diagram, you would not include that. You would probably just have tension, you would have weights, and you would have a buoyant force. We'll talk about what the free body diagram should look like in just a moment. Okay, at time t equals 0, the rope pulls the prism upwards at constant speed. At time t1, the top reaches the surface, and at time t2, the prism has been completely removed from the water, as shown in figure 2. So the thing that I really wanted to drive home on this is it says the prism always moves with constant speed. And that'll come up in just a few moments and why the graph looks the way that it does. And we can also talk about the free body diagram that goes with it as well. All right, so the graph that you're given shows tension versus time. And notice from time equals 0 to T1, you have a nice horizontal no slope line. Then you've got this weird parabolic line from T1 to T2. Then you have a nice constant horizontal slope line after T2. All right, so let's go on to what we're actually being asked for this part. So I blew up the graph for you just a little bit on the next slide. There we go. All right, and so the question just says, in terms of relevant physics concepts, explain the behavior of the tension versus time graph from T equals 0 until a time after T2. So in thinking about terms of a free body diagram for situation 1 and situation 2 from the previous slide, okay, while the prism is inside the water, you have a weight down and you have a buoyant force up and a tension force up. Okay, it's saying that this thing is being lifted at a constant speed upwards. Okay, at T equals 1, I have to double check something super fast. Okay, time T1, the top of the prism reaches the surface of the water. So as the object is emerging from the water, that's what's happening between time T1 and T2. And at T2, now the prism is completely out of the water. The base of it maybe is just right above the surface of the water. So you know at T2, there is one of those three forces that are no longer existent in a free body diagram once the object leaves the water. And hopefully you identified that the buoyant force is no longer present once the object has left the water. Okay, so why T1 to T2? Why is there a nice curvy portion? All right, let's see what I put for my answers. First off, I said as the prism is lifted between T1 and T2, the buoyant force is decreasing. Why is the buoyant force decreasing? It's displacing less and less fluid. And if the buoyant force is decreasing, that causes the tension to get greater over time, to become greater over time. Because remember, buoyant force and tension are both pointed up on that free body diagram. So as that buoyant force gets smaller, let's pretend like this is the buoyant force. It's getting smaller because more is emerging. The tension has to be greater in order to have the same constant speed while it's lifting upwards. All right, the second bullet point says that the tension is the constant force before T1 and T2 because the prism is lifted at a constant velocity and the magnitude of the forces are not changing. So while the object is completely submerged, the buoyant force is constant because remember, buoyant force is all about the volume of the fluid that's displaced. So as it doesn't matter that the object is moving upwards, the forces up have to equal the forces down between time 0 and T1. And same thing for after T2. The forces have to be constant because we're at constant speed. There's no acceleration. So just remember in something like this, I pointed out on that very first slide for question 2, or for part C at least, that it said constant speed. So you had to recognize that all of the forces, or the forces up, had to balance with your forces downwards.
Alrighty, folks, that concludes our review of yesterday's questions. But stay tuned tomorrow as we're going to work through 2 more questions. There is a quantitative question about thermodynamics, and there's a paragraph question about circuits with a capacitor that I think you're really going to like. And then we'll go over the solutions to those questions on Thursday. All right, folks, thank you very much for watching. Come back tomorrow for even more AP Prep Week.
Bye, everybody.